Okay, now we solve it, but now from high school, you know, there are several cases. And each of those cases corresponds to a different behavior. And the cases depend upon what the roots look like. The possibilities are the roots could be real and distinct. That's the easiest case to handle. The roots might be a pair of complex conjugate numbers, but that's harder to handle, but we're ready to do it. And the third case, which is the one most in your problem set, is the most puzzling, when the roots are real and equal. And I'm going to talk about those three cases in that order. So the first case is the roots are real and unequal. If I tell you they're unequal, and I'll put down real to make that clear. Well, is by far the simplest case, because immediately one sees we have two roots, they're different, and therefore we get our two solutions immediately. So the solutions are, the general solution to the equation, I write down without further ado as y equals c1 e to the r1t plus c2 e to the r2t. There's our solution. Now, because that was so easy and we didn't have to do any work, I'd like to expand this case a little bit by using as an example of how you put in the initial conditions, how to put in the C. So let me work a specific numerical example, since we're not going to try to do this theoretically until next Wednesday. Let's just do a numerical example. So suppose I take the constants to be, the damping constant to be 4, and the spring constant, I'll take the mass to be 1, and the spring constant to be 3. So there's more damping here, the damping force here. You can't really talk that way since the units are different, but this number is bigger than that one. That seems clear at any rate. Okay, now what's the characteristic equation? Look. Now watch. Please do what I do. I've found in the past, even by the middle of the term, there are still students who feel that they must substitute y equals e to the rt and go through that whole little derivation to find that. You don't do that. It's a waste of time. I did it, that you might not ever have to do it again, okay? Immediately write down the characteristic equation. That's not very hard. R squared plus 4r plus 3 equals 0. And if you can write down its roots immediately, splendid, but let's not assume that level of competence. So it's r plus 3 times r plus 1 equals 0. Okay, you factor it. This being 1803, a lot of the times the roots will be integers. When they're not, God forbid, you'll have to use the quadratic formula. Okay, but here the roots were integers. It's, after all, only the first example. So the solution, the general solution is y equals c1 e to the negative, notice the root is minus 3 and minus 1, minus 3t plus c2 e to the negative t. Now, suppose it's an initial value problem, so I gave you initial conditions. Suppose the initial conditions were that y of 0 were 1. So at the start, the mass has been moved over to the position 1 here. Well, we expect it then to start doing that. But this is fairly heavily damped. This is heavily damped. I'm going to assume that the mass starts at rest. So it's in a distended, the spring is distended, the mass is over here, but there's no motion at time 0 this way or that way. In other words, I'm not pushing it. I'm just releasing it and letting it do its thing after that. Okay, so y prime of 0, I'll assume, is 0. So it starts at rest, but in the extended position 1 unit to the right of the equilibrium position. Now, all you have to do is use these two conditions. Notice I have to have two conditions because there are two constants I have to find the value of. All right, so let's substitute, we're going to have to calculate the derivative, so why don't we do that right away? So this is minus 3c1 e to the minus 3t minus c2 e to the negative t. And now if I substitute in at 0, when t equals 0, what do I get? Well, the first equation, the left says that y of 0 should be 1, and the right says this is 1, that's 1, so it's c1 plus c2. That's the result of substituting t equals 0. How about substituting, what should I substitute in the second equation? Well, y prime of 0 is 0. So for the second equation, when I put in t equals 0, the left side is 0 according to that initial value, and the right side is negative 3c1 minus c2. You see what you end up with, therefore, is a pair of simultaneous linear equations. And this is why you learn to study pairs of simultaneous linear equations in high school. These are among the most important. Solving problems of this type are among the most important applications of that kind of algebra and this kind of algebra. All right, what's the answer, finally? Well, if I add the two of them, I get minus 2c1 equals 1. So c1 is equal to minus 1/2. And if c1 is minus 1/2, then c2 is minus 3c1, so it's c2 is 3/2. The final question is, what does that look like as a solution? Well, in general, these combinations of two exponentials aren't very easy to plot by yourself. That's one of the reasons you're being given this little visual which plots them for you. All you have to do is, as you'll see, set the damping constant, set the constants, set the initial conditions, and by magic the curve appears on the screen. And if you change either of the constants, the curve will change nicely right along with it. So the solution is y equals minus 1/2 e to the minus 3t plus 3/2 e to the negative t. How does it look? Well, I don't expect you to be able to plot that by yourself, but you can at least get started. It does have to satisfy the initial conditions. That means it should start at 1 and its starting slope is 0. So it starts like that. These are both declining exponentials. This declines very rapidly, this somewhat more slowly. It does something like that. If this term were a lot more negative, I mean, that's the way that particular solution looks. How might other solutions look? I'll draw a few other possibilities. If the initial term, if, for example, the initial slope were quite negative, well, then it would have to start like this. Now, just your experience of physics or of the real world suggests that if I start the thing at 1, but give it a strongly negative push, it's going to go beyond the equilibrium position and then come back again. But because the damping is big, it's not going to be able to get through the equilibrium position a second time. It's going to look something like that. Or if I push it in that direction, the positive direction, then it starts off with a positive slope, but it loses its energy because the spring is pulling and it does something like that. So in other words, it might go down. Could it cross the equilibrium position, come back again and do that? No, that it cannot do. I was considering giving you a problem to prove that, but I thought I got tired of making out the problem set and decided I tortured you enough already, as you'll see.